Everybody. We'll be hearing about RNtuple and Uproot from Jerry. Yes, Jerry is a graduate student at Harvard. I didn't have a introduction prepared, but do you want to say anything else?
No, it should be. Well, being a longtime user of Uproot, I've heard of Uproot and Jim's name since undergrad. So it was a pleasure to work with Jim over there last summer. Well, I guess the last summer on RNtuple, and this would be, a result presentation of that.
Yeah. So thanks. Please take it away. Try sharing screen again.
Okay, let's hope this works smoothly.
Yeah.
Can you see everything in a normal? Okay.
Yes.
Okay, so I'm going to talk about RNtuple and slightly specifically in the Uproot today. So to begin with, I have some links. If later you find it interesting and you want to, read more about it, past, future, detailed stuff, you can click on some of those. And here's an outline for today's talk. Basically, we're going to explain a little bit of the technical motivation presented by the root team and also some of their arguments and benchmark results and a rough timeline of adoption. It's going to be detector collaboration dependent because they get to decide what they actually want to use, and some of more comparisons. And then on fourth point, some of the benefits for us from a technical developer perspective. And then five would be the most bulk part of the body, where I go through a RNtuple example to show how the file format itself works, and then some additional comments. By the way, if anything's unclear or just technical whatever, please feel free to interrupt me. So why a new thing, right? So we know and love, maybe don't love, but love T-tree for it has served us a long time. From what I can tell, and from talking to Jim and some of the root team, it boils down to some of these reasons. First of all, T-tree has a lot of special cases, in terms of if you store something in a container and how many levels the nesting there is, they kind of don't follow the exact same pattern. So you can't just deal with it once and then expect it to just work for all the nesting. And as a result of that, these implementation sometimes leads to inefficiency. For example, one of the well-known examples is when you save a root T-Lorentz vector, you're wasting half of the bytes in your branch because of the T-object metadata. And there's some of just purely due to historic reason, like they use big NDN, so every time you read anything, you have to bit swap them. There's also a lack of concepts of cluster, or people call them row group. So it's difficult to bound your memory. Usually what happens is they are leaning on the small chunk size, which leads to inefficiency in reading. So some of these will be, I think all of these are addressed and changed in RNtuple, and then they throw in a bunch of other stuff. But these would be, I think, the main motivations. As for the timeline, so from a user perspective, what you are expecting from root team's proposal, it should be a run 4 technology, but they expect some people to try it during run 3 at various stages. So probably not like a collaboration level. So by not collaboration level, I mean, if you are on Atlas, maybe XAOD probably won't be replaced with RNtuple just yet. For CMS, I don't know. I see no reason why nano AOD couldn't be replaced, but whatever's up AOD maybe not, just because there has a lot of root specific hacks to store, collections of objects that have reference to each other. There's like a customized way of doing stuff. So don't expect that to happen, but maybe on analysis level, the root team was expecting people to try it during round 3, and then round 4, maybe everything will be RNtuple, what used to be T-tree. And on the performance side, they have done some studies, which I think there's a link in the first slide, but they have compared reading speeds, and I've heard that they're doing writing performance studies recently, but I couldn't find any slides just yet. But here's one for the reading. You can see that under different compression scenarios for nano ALD data on the SSD, RNtuple is visibly faster for most of the compression algorithms. So that's a good thing. And some of the conceptual difference in terms of types. So if you think of a T-tree, people usually avoid storing complicated C++ structure in it, right? I have never seen pairs of variants actually. I think variance is illegal. That's true, yeah. You can't really write variants in a T-tree, but I heard that it's possible for pair and tuples. In any case, it's rarely done, and people generally have a feeling of, just couldn't trust T-tree to handle complicated data all the time correctly. But RNtuple changes that in the sense that the way these containers nest and compose with each other is really systematic. So you could put more faith in it, and more importantly, it at least works. But yeah. So this is, I guess, is half user, half developer perspective. But when you think of so if you're an Uproot user, right? When you think of all the possible data the old root can read and write from, into, and from a T-tree, it's definitely a superset of what we can read, and it's even a bigger superset of what we can write in Uproot. So that creates a lot of unexpected, just bad experience. Like someone's trying to do a study, but they realize, okay, in the end, they have to hand it back to root, and they couldn't actually write that data type the root framework is expecting or whatever. So just a lot of friction, and also a lot of hacks goes into reading, and especially, I guess, writing of the old T-tree file format. And it's a constant struggle. Like every few months, you see someone say, okay, I have a file, I couldn't read it, why is that? Something like that. For RNtuple, it's gonna change. One of the biggest reasons is because it has a specification. So it can't just do random stuff at the corner of some edge cases. So the best case scenario, someday, when the spec is fully stable, when the root is stable, is that the root, Uproot, or any other alternative implementation in different languages would be 100% compatible in both reading and writing. It's certainly possible because it has been done for some other formats. Think of maybe Apache Parquet or Apache Arrow. But for now meaning end of 2022, there's some unimplemented stuff in the RNtuple spec, even for the C++ root, namely pointer stuff. So those are probably needed for large experiments, raw-ish data. So that's to be done. But already, for what the C++ framework can currently write out, I think that this may not be technically accurate, but from what we can tell, we can already 100% read them. Which, if you think about like how many years we've put into T-tree, reading, this is a huge improvement given how much time how little time we spend on this, and it's already basically done. So it's just a really promising fresh start. So come back a little bit to the concrete RNtuple. I want to, in the following maybe 5-6 slides, I want to give an overview of just a taste of the technical composition of RNtuple. I think it's more useful to give such a introduction to RNtuple than to T-tree, because RNtuple is actually very modern in the sense that there's a lot of other file formats that's in one way or another is basically same as RNtuple. So if you learn T-tree, you only learn T-tree because there's nothing like T-tree, and T-tree does things very massively. There's no design pattern to be learned. But RNtuple is a good thing to learn, I think. Once you learn RNtuple, you'll understand a lot of different file formats just by remapping some of the terms. But in any case, to understand how RNtuple works, we still have to deal with the legacy root file a little bit, just because it's still in a root file. So I always say that the root file is more like a file system because it's a bunch of bytes that's self-descriptive, and you can have directory and lookup by names, right? It's basically like a folder sitting on a file system, except that it's a contiguous bunch of bytes. But even in those contiguous bytes, the files are not actually contiguous. So, it's more like a file system on a disk. Just the disk is a chunk of bytes. Anyway, so RNtuple itself is pretty independent from the root legacy parsing logic, I would say. But just to warm up, I would start from the root. So the entire root file is represented by the whole width of this this chunk. And at the very beginning, there's 100 bytes or so header. And then after that, there's a header T key, and then more bytes. So that would be the rest of the bytes, like gigabytes or even a terabyte of root file. So inside, before that, here's the notation I'm going to use when I talk about the files. So this would represent, you can see the mouse movement, right? I hope.
Yes.
Okay, so this will represent just bytes on disk, and this would be like an interpretation of what those bytes mean. And I would try to put the object name here, just in case you have to search it. So I would try to put the real object name here, and I would also try to put the real field name here. But sometimes I would omit the irrelevant ones because. And whenever I have a pointer like this, it means this is the offset, and it points to the offset somewhere in the bytes on disk. So for example, if the seek says 2008 and 4, it means that there's a different object here that starts at 2084. So from a root file, the task is to find the RNtuple, right? So we can just forget about how root does things and then focus on RNtuple. So from the header key, which is near the beginning of the root file, you can find something called a directory, which tells you every single object by name in a root file, kind of. And noticeably, there's probably a thing named RNtuple, or actually NTuple, and that will point to the object that is RNtuple anchor. So there used to be a lot of interaction with a T directory and another thing called streamer when you read a root file, because essentially you just try to read, and then it says, okay, you need this thing, but you don't know about this thing. So you have to go to the streamer and then the directory to look it up, etc. None of that has to do anything with RNtuple. For RNtuple, you just need an anchor, and then everything starting past the anchor, everything will be different. So we only need this very shallow logic of finding it. But anyway, so anchor contains some of these information. I'll explain what they mean in the next slide. I see. I put this line on the wrong place. Oops. This was supposed to be in the previous slide where I was explaining what T-tree was incapable of. But yeah, so the anchor. So the first step we already done. We found the anchor, which is a gateway to RNtuple. And then the next step is to find the header and the footer from this anchor. So there are 3 fields related to the header that we need. And this is a general pattern, so I'm just going to talk about it once. Later, most of the things that has anything to do with reading real bytes have this logic, but I just want to show it once again. The point here is to show the most common pattern in RNtuple and other file serialization applications. So the seek, as I was explaining, points you to offset in the file, and the number of bytes tells you the number of bytes you're going to read starting from that seek point. but the length of the header tells you the number of bytes after decompression. So by comparing these two numbers, you can tell if those bytes you just read were compressed or not. And if it were compressed, of course, you have to decompress it. But repeat this, for everything basically. So you do this for the header. You have a header. You parse the header. Header contains things, points to other things. You parse those, and you read what those bytes you decompress the main according to the specification, and you assemble like a metadata structure. And in the end, the metadata structure and schema looks something like this. So just to repeat the steps we did before. So first is to find the anchor. And the anchor would point you to header and footer. And then you parse those. The header will contain something called schema that I will explain in a second. And then the footer will contain something that points to another object called page list. So the main point we want to demonstrate that in the following slides is that the schema we parsed here is going to be compatible with awkward array, awkward form maybe. So if you're familiar with that, we will you'd be happy, and we will show that how we read, all sorts of composed types by using awkward facilities. So let's look at the concrete example now. So assuming you have a RNtuple that contains the following data. So you have three, maybe you would call it branch or column. Let's just call them fields because that's what they are. And I will explain the difference between fields and columns in a second. But this thing has three fields. And I have put the element type here just for clarity. So the first one is just a trigger, which contains Boolean. This is a struct. And then this would be a jagged integer. So naively, we would say, okay, this table has three columns, which is correct. But if we want to kind of make the nuanced points about what is field and what is column, we will see that it actually has 6 fields and 5 columns. And the thing that we see and we address by name are actually field. But don't worry, this is just to give an example and the different variations of different types so we can see how they work in reality. So given this concrete RNtuple, we can look at the fields and column metadata collection. So viewed raw, they look like this. So this is the promised 6 fields I was talking about. And you can see that some of them have the name of the field as the type, right? So the met was just called met.
Jerry, may I interrupt for a minute and ask you
Yes.
back to the last slide because I'm not so good at abstract concepts. So I see 3 rows, 2 columns. You've got a struct which says, so you've got E and phi, 530 and 2.3. And then associated with that, you have 3 lepton PIDs, 11, 13, minus 13.
That's correct.
In the next row, you have an energy and phi, but you only have 2 lepton IDs. And in the third row, there are 4 lepton IDs. So I've got no idea what these are supposed to represent. I've got no idea, like concrete, what are these? This is from a world very different from mine.
Oh, right. Sorry. So, I mean, each row would be event, right? So we're talking about event. And then this column would be the missing transverse energy. So for that, we only have energy and the transverse angle phi. And the PID is supposed to be the particle ID for leptons. So in this event, we have a electron and a muon and an anti-muon. In this one, we have electron and positron. In this one, we have 2 electrons and 2 positrons.
Okay, so these are, so each event has 1 missing ET and some number of leptons.
Right.
Okay, that's what I was trying to understand.
Right.
Thank you.
Okay. Yeah, no problem. So yeah, I mean, this is made up data, but the point is to show different kinds of data we encounter. Like a scalar is very common, something like a struct we usually use because Lorentz vector would be a struct of 4 numbers. I don't want to put 4 number here, so I made up something called ET struct, a Met struct. And then of course the jagged array is also common because of the variation in number of particles. But yeah, so that's a good question. Maybe I should have put event number here for clarity. Okay, so this is the promised 6 fields, and you can see that some of them, the first 3 of them actually have the same name that we already saw, which is what the, if you're a user, you're gonna call them what they are: the trigger column, the met column, the left PID column. It's just that they're fields, and we'll talk about how they one-to-one in a second. But we can stare at this for a second. So there's something called the parent. So this is the parent of this given field. So each line here has an implicit index. So this one would have an index 0, and then this one has index 1. This one has an index 2. And you can see that when the parent is itself, it means that it doesn't have a parent. It's a top field, and that's how you can tell that, okay, these 3 are actually what users gonna see, because these 3 are the only ones that have parent equals their own index. So we just kind of play this type of game with this, and then next collection that's called column. So column here, the field ID is kind of like parent, except that it points to a field. So this is the column collections. So the field ID is referring to elements from the last list we were looking at. So in this case, this column record is associated with the first field record that we were just looking at a second ago. And then the n bits records how many bits each of the event, or I guess each of the data contains. So we know that the first field is a trigger, and then that one's a Boolean. RNtuple stores Boolean as single bit. So this n bits is 1. So this is the kind of pattern. So we're gonna come back. So now we come back to the way to look at the, so these are the raw representation of the fields and columns or whatever. It's really hard to read because you have to remember what number is what and then try to draw lines in your head. If you're familiar with awkward, here's a better way of representing it. So we can represent all the information we were alluding to in this tree-like structure. There's a slight typo here, which is this PT should be it shouldn't have a name. This one should be _1 because it's PID and it's not a struct, but just a typo here. But otherwise, we can see that from the top level, we see 3 named things, awkward form. I'm just gonna call them awkward array. So we see 3 awkward arrays. One of them is very straightforward. It's just primitive data. So Boolean is a primitive data. So it's directly associated with a single column. And then the column is gonna store the data itself. And the field here is responsible for metadata, like for example, the name of it, the type name of it, whatever. Then we come to the second top field, which was the met. So this is actually represented by 2 separate child fields, because the met has 2 inside the struct has 2 fields, and each of them have a name. So you need 2 more fields to keep track of those names. And then they are the ones that have associated columns, because fortunately enough, the field itself is just primitive types. So you get a column. If this were not a primitive type, like you have a struct of struct, then you can imagine this keep going down. And there's no edge case. You can keep doing that as long as in the end you come back to some primitive representable types. And then same thing for the phi field in the struct. And then lastly comes to our left PID. So this is a singly jagged array. And the common way of representing it is we have an offset array and then we have a content array. Again, the PT is a typo. This should really be unnamed column because it's just data of PIDs. There's no name associated with it. But here the offset index is int32, and the data is whatever data you have here. So imagine you're not storing PIDs. So actually, here's the different typo. This should have been int32 because PID themselves are integers. But yeah, but imagine you're storing lepton PTs as a jagged array. You would have this unchanged, and then this would be _1 float 32 or maybe double. And here, if we can count how many stuff we have. 1, 2, 3, 4, 5, 6. I don't know why it has 7, but 1, 2, 3, 4, 5. So this is the promise, the 6 fields and 5 columns, I think. If you're not familiar with awkward form, it's also fine. It's just a tree representation, and hopefully that was a little bit helpful putting Y fields and columns together. A different way of looking at them, we can also just look at them as
could you go back a second?
Yes.
Could you go back? I see the 5 columns. I guess I missed. It's 6. What are the 6 fields again?
Right. So I think there's 1, 2, 3 for the top fields.
Okay.
And this one is actually not a field.
Oh, that's what I missed. Okay.
Yeah. Yeah. Unfortunately, to make this right. There's
whose terminology is the field? Is that Root's terminology?
Yes, the field column terminology is RNtuple's terminology.
Okay, so
right.
Since you're trying to map this onto awkward, it doesn't quite match because this list offset array doesn't have 2 fields, it has 1 basically.
Right. So
even though it
reality,
has 2 columns.
Actually,
yeah.
Right. In reality, actually, awkward doesn't care field and column. Awkward just needs to know that for every, so let's say list offset array, right? It needs 2 child things. It just care what are those 2 child things are. And in reality, you can lump these together. You can lump every column primitive NumPy array together, and then awkward would be fine with it. This distinction is to help us visualize where the columns attaches to in the awkward form. Yeah, sorry, this is slightly mismatched.
Got it now, thanks.
Yeah, okay, so yeah, so here may be a different view, and we can easily count how many things. So whenever you see a leaf, that means a column. So that's a leaf field that's directly 1-to-1 has a column associated with it. So here we can see that you have 1, 2, 3, 4, 5, 6. Wait, what? Whoops. Again, column is easy to count. You can see there's 1, 2, 3, 4, 5 columns. For the field, you have 1, 2, 3, 4, 5, 6. Does that make sense?
I think
so each of the leaves.
I think it'd be sufficient to say that there's some mapping between the there's a deterministic fixed mapping between the RNtuple concepts of fields and columns and the awkward array concepts of leaf data and indexes. There's a mapping between the 2 languages, and it's 1-to-1. You can always translate one. Like it's a bijection. You can always turn one to the other and back without losing any information. That's I feel the most important thing here.
Yeah, I agree. Yeah, there is. It's just that there's some bridging to be done in the middle, of course, because they're 2 different things. But it can always be done. And I was trying to make them.
Just out of quick curiosity, how expensive an operation is that translation?
Oh, no. It's done once at the very beginning of the parsing, so it's like it's negligible.
Okay,
because
is it
the
order?
algorithm.
Sorry, go ahead.
sorry, I was just gonna say that the algorithm is kind of probably maybe O(n) squared, but n is the number of fields you have, but usually you only have like 1,000 at most, right? 1,000 or 2,000. It's not
Okay.
gonna.
Okay, so it's not the length, it's not but the number of rows, it's the number of
Oh yeah, no.
fields.
Yes,
Okay.
yes.
Oh,
Yes,
that's all right. So that means that the data that's stored there is used directly by
Yeah.
Awkward. You don't actually have to, translate those into starts and stops or some other format. It's the same.
That's correct.
Okay, perfect. Thanks.
That's correct. Yeah, every single one of the representations has a unique mapping awkward that already can use the exact same underlying data directly. So there's no data kind of translation other than decompression, which you always have to do. But
Of course.
yeah. Okay, so now we're gonna do them just so it's absolutely clear how the association works. So again, we're looking at the first field that we're looking at, which has the parent PID pointing to itself, right? So this is the way you know that it's end of a field, parent, daughter, chain, whatever. This is the end of it. It's a top field. And then you look at the column. There's one column that has a field ID pointing to this. And you know that the type of bit and the size is 1. So for this trigger field, you have one field and one column. Done. Then for the mat, it has 3 fields, because first you need a struct, the umbrella struct mat, and then you have the 2 legs inside it. That one of them is energy, and then the other is phi, and then each of them is a primitive type. So you have a column attached to them, and this is how you get the mat field. So you would have 3 fields and 2 columns. And this is where I would say, notice that the data is never associated with a field. Data is always associated with column, because column stores primitive data directly. And you can always have fields that just doesn't have any data directly associated with it, right? For example, this struct umbrella field. The only purpose of it is to structure the other fields and column, so it makes sense and appears as a struct field in the to the users instead of separated columns. And lastly, here's the I think I heard a question.
I think you're going to answer it on the next page. Go ahead.
Okay, yeah, no, lastly, it's the offset thing. So if you're not familiar with the offset content encoding of a jagged array, here's a quick demonstration. So assuming your real data looks like this, so you have first event that has 2 entries in it, second event no entry in it, third event 1 entry in it. The offset column of this array would be 0, 2, 2, 3, and then the content would be just the content concatenated together. And the way to interpret is that the first element is 0 to 2, which is 11, 11. The second element is 2 to 2, which has no element, and then the last element is 2 to 3, which has 1 element. So to encode a singly jagged array, you just need 2 arrays, one for offset index, the other for the content itself. And that's exactly, yes, go ahead.
No, sorry, there's a lag, so I thought you were done. Finish the slide and then I'll ask the question.
Yeah, so I was just gonna say that this is how exactly the left PID is stored. So the left PID itself has 1 column associated with it, that is the offset. So the type name in RNtuple is called index 32, signaling that it's an index column, not the data column, even though it's just storing integer numbers. And there's a child field associated to this as well, which stores the actual content. And then for that, of course, you always need an additional column. But yeah, you can see that this is you can reuse all these column data. The only thing you need to do is piece this to feed it to awkward form, feed this to awkward form, etc. which can be done at the very beginning at the parsing time. And the question?
Yeah, I just want to make sure I understand. So right from the file, it's impossible to do random access into one of these columns without interpreting every single row before the row you're interested in. Is that right?
It's so the rows are stored in chunks. So in fact, it is definitely possible to read a random entry without reading the entire file, but you would have to read the entry around that row.
Okay, so
And
you have to read the offsets for the entire chunk up to,
Yes,
and
yes.
then run that calculation to, okay.
Yeah. So that's where the, if you remember, the cluster or the row group comes in. So a cluster is a minimum unit of rows you can read in order to know what event is what event number in a given field. You can read fields independently. You have to read all the fields together.
Can I add something?
Yeah, of course.
I think so. You can actually read just one entry. You don't have to read the entire cluster. But it's just that for a collection, you always need to read two elements from the offset column. So this is the reason why there are offsets and not lengths of the vector. If there were length of the vector, you would need to read everything up to entry numbers such and such.
Wait, okay, Jacob, I don't understand. Okay, his one offsets colon looks like lengths to me, not offsets into a column.
We're making different points. We're making
Oh,
different points here.
okay.
Once you have decompressed the offsets for an entire page of data, then you can do random access into those offsets because they're offsets instead of counts. That's the distinction.
Oh,
that,
now I understand. I now understand. This offsets represents a row with 2 items, a row with 0 items, and then a row with 1 item. Got it. Okay, that was my error. Thanks.
Yeah.
Now this makes a lot more sense.
Right. But then there's the other issue that's true of any columnar data, that it comes in chunks, and you have to decompress that entire chunk in order to use it.
Yeah, no, that's fine. That part I understood.
I see. You were asking about the indexing is ON or O1. Yeah, it's O1. It's O1.
Yeah, no,
you have
exactly.
to read the offset one. Right. Got it. Okay, I see. I thought you were
Right.
asking about the reading. Okay.
Yeah, no, I was just confused. I understand now. Thanks.
Yeah. No problem. Yeah. So I mean, RNtuple does this because it was done in the T tree as well, and then awkward form has a ready to go solution to encode this type of array. You just give it offset. If you give it content, user sees a jagged array. You can do all sorts of awkward goodness with it, and that's all good. So just to put this thing together, what we know so far. So the RNtuple headers and stuff tells you, here tells you how the fields and columns should be interpreted. Giving you the schema type tree. The footer. So if you remember, I was saying that the footer points you to something called page list. So this is where the real data themselves live. And they live in units called pages. And here you see this very nested list. So actually, this is a triply nested list. In the next 2 slides, I will show you why this is needed, like why there's 3-dimensional in this thing. But all it matters is that in the end, you read actual data from something called page, and they're kind of like just raw bytes of the primitive types that you are allowed to store. And then you have to, you have to pair with what you learned before in order to correctly interpret them. And to explain why there's a triply nested list, imagine this. So this is a pretty dense plot. So I will go slowly here. But before this, is there any question on this slide? Okay. So the reason you need triply nested list is because there are 3 directions for things can grow. So the outermost is you could have more clusters. So a cluster is good for some number of events. You don't want the cluster to be too small, because then as you read the events, you are constantly dealing with the metadata. But you also don't want it to be too big, because then a single cluster won't fit in your RAM. So in any case, you would need more than one cluster. So the outermost list is responsible for growing of clusters. Then the second, the one list in, it's responsible for more columns. So this corresponds to when you have just more data columns, either because you have more fields or you have more complex fields, right? But you need more columns. And since users are not always reading all columns, you better have that as a indexable things. Like NanoAD has 1,400 or 207 something branches. Not everyone's reading all of them at the same time. So you have that dimension to responsible for the number of columns you have. And then the innermost is the pages. Again, even though you can decompress a page at a time, they don't by themselves, they don't actually represent anything, but it's still a good idea to have a page not too large, because I don't know, sometimes when you write the data, the thing crashed or whatever, you would have some data there, or it would be better for relocating. But in any case, this is a very common pattern to just have, not a single page for all the things in them. So that's the third dimension of growth. So basically, that's why you need a list of lists in this thing. And right. So okay, there's technically a even outer list, but that one is distinct enough that you don't have to think of them as together. So each page list that you were looking at, the list of list, is responsible for a cluster group, which has multiple clusters in them, which is why there's a cluster dimension. But in a very rare case where you might have more than one cluster group, I don't actually know what's the specification limit of how large a cluster group is, but I think it's pretty big. But in any case, if you have more than one cluster group, you would have more than one page list. And in that case, you just look for a different list. And then whenever you need an event, so let's say you need the 1,000,000th and the 324 events, you would find the cluster group, and then find the cluster in the cluster group, and then read that cluster. And then from the offset, go to the event within the cluster, and then give that to the user. That's the minimum amount of things you need to read in order to get a specific event. You still need the entire cluster, but you don't need you go find the cluster group, find the cluster, etc. So, okay. So after this is just some comments, but is there any question for me at this point? Unfortunately, I cannot see the screen, sorry. So I can't see people's faces.
Yeah, maybe I don't quite get why one needs the pages in addition to the clusters. Can you explain it again?
Right. It might be a better question for Jacob, if Jacob's still here. I don't know who was.
Yes,
was
but I didn't.
Yeah.
I didn't get the question.
The question is, why don't we just store this as a one page? Why do we have multiple pages? Given that we can't read one page out of it to get a random access event, right? Like if I need, let's say, so this cluster, let's say, is responsible for entry 0 to 100. If I need event 60 in this column, I can't really find the page where it is at. I have to read all of the pages and count from the 0 to this anyway. So the question is, why is that this is not a single big page?
In practice, it doesn't make much difference, because the way it is stored on disk is the pages are all, so pages of a single column in a single cluster are stored consecutively. So it would still be one read call to get all those pages in the cluster. The reason is most likely memory when you write. And if you have infinite memory when you write, you can write bigger pages.
I see. Because I see. Because when you are writing data, you are storing all the pages across all the columns in memory before a write, probably. And then you don't want those to be too large. Then you may run into troubles, I guess. Yeah, I see.
So those are essentially compression units.
Yeah.
Because you need to like buffer them in memory before you can compress them. So that's why you want to subdivide the cluster and such that you can make it large, but still avoid to need too much memory.
Right.
Yes.
Right. Yeah.
Thanks. Yeah, that explains it.
Yeah, I mean, when reading though, right? Like it doesn't solve your problem. Like if the memory doesn't fit for the number of columns multiplied by the cluster size, it's just not gonna fit because you can't break it up. But yeah, for writing, you can, because you're doing this append event style of writing. Then yeah, even if you're writing more columns, it's possible for page size to help you. I see. Yeah. Okay. So wait, any more questions?
So I can ask a really sort of naive question, because I'm not expert on this at all. And as Jim knows, I like very concrete use cases. So do you have any examples of code where a user is reading an RNtuple in Uproot and doing something with it?
If you're familiar with the T-tree syntax, so you have a T-tree and then you dot arrays and then you give a bunch of names, that just works. That just works on RNtuple.
Exactly.
So it's exactly that. Yeah, no, it's exactly the same. So for RNtuple, you don't have to worry about anything. The same syntax works. So entry start, entry stop, given names of the fields you can see at the top level, it's gonna give you a awkward
So
form.
from the naive Python user, I will open a file with Uproot. So I'll have dot open, right?
Yeah.
And then there is a list of the names of, I guess, what the leaves are, or what. So then you do it.
The root.
You do something with a subdirectory. You give it the subdirectory within which is probably the tree name, and then you give the name of variables, and I read those into a Python dictionary where I've got a key and a value, and so I use as the key, I use the root tuple name, call it root tuple, and then I give it a Python name, and then I do Python work.
Yeah, I think that just works. So so I mean, usually what you index the opened root file with a T-tree name, right? You just swap that to RNtuple's name, and then you the same dot arrays, start entry, stop entry would just work.
Okay.
Yeah.
So it'd be for a different audience, it'd be really useful just to show something like that.
Right. I think I used to have a slide, but I don't think I have now, unfortunately. Yeah. Sorry.
And then it would probably be useful again for naive users where you've got an example which uses a more complicated version of a data structure of the sort you've illustrated here. So I'm not sure how you would look at the missing energy and then look at the lepton IDs in a single event. From a Python code perspective, I'm really interested in seeing what the Python code looks like, because most end users don't care about how things are organized logically under the hood. They just want some simple examples that they can cut and paste and repeat.
Yeah, that's a good
Right.
point. Yeah. There are examples in the unit tests, which I was thinking of going and looking up. But at this point, the short story is that Uproot RNtuple interface matches the Uproot's T-tree interface. So as Alex said, naive user wouldn't notice a difference at all. Probably, yeah. It might, they might not run into any different. There are, of course, some differences between T-tree object and an RNtuple object that if you were to dig into them, you would see those differences. But if all you're doing is you're just taking this object and asking for awkward arrays, you'll get awkward arrays, and then you continue your analysis as it was before.
Right. The assumption is that user knows how to manipulate the awkward array for analysis because we are forced to do most of the things in like this columnar style, and awkward array facilitates that. And hopefully anyone doing mildly complex analysis already use awkward arrays, those transformation and utilities. So if we just hand the user a fully qualified awkward array, which we do, user can continue to do what they used to do with a T-tree.
Well, I'm even thinking about not a user who what they used to do, but just simple examples for new users. We do have new users every year, and then there's some who forget every year. Yep.
Mike, those exist. There are whole tutorials on how to use awkward arrays, how to load awkward arrays from files, etc. There's so much documentation out there. It's awesome because I can never remember when I have to take a break for a couple of months, and I just go to the web and there it is. So I think that part is well done. I'm finding this talk fascinating because I've only known about RNtuple at a very high level, and it's very nice to see some of these.
I think this talk is great.
I'm
just saying that the only thing I found missing was, what a naive user would need to know.
Yeah, that makes sense, actually. Yeah, should have a some of the dot array example just to show user they don't have to worry about things break. They still can get the data directly.
Okay. So
okay.
Thank you.
I think we're kind of into the questions now because we've got about 5 minutes left, and Alex and Doug both have questions. Start with Alex.
Yeah, thanks a lot. This was really interesting to see. Apologies, my question isn't super related actually to all the technical details here, but it's quite high level. Is there any utility that exists that can take an existing file that contains T-trees and translate that into some RNtuple version that could be used for, say, testing the performance and just trying out what changes?
It's a fantastic question. Jim and I were looking at a repository by root team that was doing some IO stuff, and we think there is one, but you have to kind of yeah.
There is actually one that got just merged, so it's fresh and new. It's called RNtuple importer. It's part of the root sources, and this does exactly that. So you take a file with a tree and convert it into a root file with an ntuple.
Okay, awesome. Do you have a link to where I can find this by chance?
Yes, but I'm on the phone, so I.
Okay, I will look at this out.
Just write to me. I can send you the link.
Okay, thanks.
Okay, Doug, your question?
Yeah, this is actually a request. Really nice talk. This sort of fits on with the idea of having some complex enough examples that we as a site can actually use to instrument our physical storage and show the benefit to the users of T-tree versus RNtuple versus RNtuple on object store versus shared POSIX file system, et cetera, et cetera, et cetera. But really for essentially benchmarking and instrumentation and measuring from a data center point of view. It's more a request than anything, but we're happy to collaborate to do this, but to push the ball along.
Okay, yeah, that sounds like something that we should do with Jakob's team. To do those performance tests in all the different ways.
It sounds to me like one of the first things Doug would love to see are very large RNtuple samples, which could then be played with to first order. And that's a lot along the lines of what I think Alex was going after, if I can read between the lines of Alex's question. And sorry, Alex, if I misread you.
No, this is very much correct, yes. I think you're reading between the lines correctly. But I mean, I think so, like, for sort of purposes of, for example, doing this with analysis crunch challenge, I think this is also something the root team is doing towards JEP. We need to talk with each other to see exactly what can be done there.
Liz, question?
Yes. So I think it is a little bit of a challenge to go from where the RNtuple features I saw now to being able to, say, represent the EDM of CMS. And since we do have to move to RNtuple by run 4, I think we're kind of missing a program of work here. So, but I don't know whose program of work it is. I guess it's CMS's, but it might be that it would be better if everybody is going to have to rework their EDMs to do things in common where we have common needs. That's kind of my comment. And I mean, specifically what I'm thinking about is, you know, you have a track, you want a pointer to all of its hits, right? And so there do need to be persistent pointers. And the way that the tree did that, we didn't really adopt it because the implementation came too late, right? So we have our own EDM refs, right? And I think a lot of other collaborations might have that as well. So maybe this time we can all do it together and make it part of the actual file format. What do you think?
It is. So something that you know, when we're looking at it from Uproot view, we haven't shown is that the RNtuple structure has several abstraction layers. Uproot and Awkward Array go up to the abstraction level of, you know, the individual fields and columns, like what Jerry was showing. But RNtuple itself in C++ has an additional abstraction layer on top of that takes these like raw data structures and maps all the C++ types to them. So that goes a long way toward representing data formats that are already defined in C++. And I don't know if Doug wants to answer this.
You know, I think just generically what you and Liz are talking about, we really, because there's an effort inside of Atlas that's doing exactly this, just trying to swap out T-tree for RNtuple for most of our data formats just to see what happens, as opposed to rewriting the EDM from scratch. But, you know, it sounds to me like we somehow need to get everybody in the same room, because my suspicion is lessons learned will really help each other out and cut down on the time it takes to get this done.
Yeah, I think so. And also sustainability, because if we're all using a similar solution for the same problem, then we don't have to have 3 different groups maintaining it, right? An Atlas, a CMS group, and another group.
Is this something that can be done under the auspices of either HEP CC in the US or the HEP Software Foundation more globally?
I think the Software Foundation could help make collaborations, but it doesn't have funding itself, right? So HEP CCE sounds like a better way to go for that. You know, they have an IO thrust already, you know, because you were at the meeting yesterday. So I think it aligns with that. Yes.
Yeah, I think the very first thing to do is to get people talking informally and then figure out some sort of a formal structure, because first you got to make sure everybody's interested and it will be worth their time.
Yeah.
And
I
suspect we can't decide that here. Yeah.
Could do. Yeah. Okay.
Actually, on this point, my mind is sort of turning around this, if everyone will be interested in if you're adopting RNtuple, this is a thing that will need to be done. And I think that this is a generally agreed upon thing that RNtuple is the way we're going with root file formats. You know, run4 is not going to be in T3.
Agree, Jim. But
Right.
you know,
So it's-
collaboration is more complicated than just oh, we're all using root, for example, and you know, you can see how the collaboration worked out there.
I think I've heard from well, anonymous Atlas high-ups that they think RNtuple is not going to happen just because they're not going to do it, in the sense that nobody's just going to do it, right? Like you. So I don't know. It's certainly, I think it's certainly not just people agree to use something and it will happen. It needs active push.
Yeah, okay. So it has to be pushed, of course, and people have to devote resources to it. And Atlas is certainly doing that, and I know that from firsthand experience. And if you look at all of the Atlas plans that they've put up in the LHCC, so this is a fairly formal review. So you know, if somebody gets up and says something there, it's almost certainly been vetted at multiple levels. RNtuple is, you know, baked into the plans for run4. So I'm not sure where you're getting that information from, but it certainly runs counter to everything that I see within Atlas. And I don't know,
Yeah,
Doug is here from Atlas, and others may be
But
able
that
to
may be a
also
run
shed
3
further light.
versus run 4 thing, Gordon.
Yeah. Well, run 3, run 3 was supposed to be experiments, which I think is exactly what the RNtuple production schedule or development schedule is, right? Is that right now is the time to build the tests, really work it out so that when we convert to run 4, we can be confident it's going to be solid. And, you know, run 3 is the perfect test bed for that.
Yeah, I represent the viewpoints of the common software to the LHCC, and I can confirm that for Run 4, Root has told everybody that you know, T-Tree is going to be kind of a legacy read-only sort of support. That if you want to write data in Run 4, it has to be RNtuple. And nobody said no to that. So if Atlas is secretly thinking, no, we'll make the
Atlas is not,
support.
I don't want this rumor to get going here. Atlas is not secretly thinking that. All right, let's just stop with that.
Not like
right.
Atlas is going to
that.
HDF5 like Dune.
Oh, okay, we should rate it in because.
Yes.
So Liz, was anyone from LHCB even at the meeting?
Yes. The level 1 coordinators all go to the LHCC computing.
Who is the LHCB level 1 coordinator? Is it Conchezza or is it someone else?
You know, I don't know right off the top of my head, and I'd hate to misspeak, but I can easily find out because I can look at the Indigo and get that information to you.
I appreciate that. Liz.
The level 1 coordinators are asked to present at every one of these meetings. That's why I just want to make sure I have the most recent one.
Yeah, when we is our computing coordinator, but I don't know. But he's not one of the technical experts.
So, Mike, when the LHCC software review happened, LHCB presented and was there, and was exactly there during this discussion that Liz mentioned about T-Tree getting effectively retired. And while I don't remember the words that were said, they basically were on board with the common plans of moving to RNtuple. I think the community knows this is coming. Whether or not the community is devoting enough resources to make it happen in time is a completely different question. But
this is a really interesting question for me, and it may be related to appropriate activities during a second iteration of IRIS-HEP, for example.
Oh, perfect. Okay.
Yeah.
Yep.
In which case I should learn more about this because I don't know anything.
Okay, always good to learn more.
Well, absolutely always good.
So just as a reminder, we're at time. Does anyone else have any other questions? Catch us while we're still here. Oh, by the way, Alex put a link to Atlas Software and Computing LHC, HLLHC roadmap in the Zoom chat, which will go away when we end the meeting. Any other questions, comments?
Yeah, I mean, I would have one more technical one. It seemed to me like when you mentioned this, the stuff, how RNtuple is structured, that it would be now also when you read it with Uproot, you have now much less overhead reading these really wide trees, because I think that's currently a little bit annoying if you have like things like an DoD first slide where you have like thousands of branches, then can take seconds to just read the T-tree object in Uproot. So my understanding would be that this would also be much nicer now with Uproot, RNtuple. Is that the case?
We haven't benchmarked the schema processing speed, but it's my understanding that when user doesn't need all the columns, they should say so ahead of time before we processing all the metadata. But certainly, I think, correct me if I'm wrong, Jim, but chasing stuff in TStream or T directory sounds like it's more expensive than just going through two lists.
Right, although we avoid reading TStreamer info when we can. So actually, on this point, Nikolai, the overhead of just opening the T-tree, or the overhead of just opening the RNtuple, where you're saying it can be a few seconds for thousands of fields. I don't see any reason why that would be different here. Here, all of this parsing the headers and such in Python, just like the headers of a T-tree are parsed in Python with Uproot, that part is the same. But you can decide not to read the full data sets from all columns, but you still have to get the metadata for all the columns. That part isn't different. We haven't actually benchmarked that, like Jerry said. Maybe the data structures in RNtuple are sufficiently less complicated that parsing them in Python is quicker than parsing the equivalent T-trees. But then we'd be talking about, is this going to be a factor of 2 or not? It's not going to be many orders of magnitude faster for just opening the object, the order one time.
Okay, that's something we watch closely, I guess. I mean, when the analysis gets more complex, that overhead doesn't matter so much anymore. But you might have use cases where you only want to read a few branches, and then you spend all your time just reading that metadata.
Yeah, in that case, I don't know if Uproot is missing that API or not, but it definitely should be possible to partially process the schema for both T-tree and RNtuple to make it faster.
Maybe RNtuple have to table but
RNtuple would be easier because you just by name, you cut out every unrelated fields and you only look for columns related to these fields.
Keep in mind, we're making a distinction here between reading whole columns. We can always avoid reading whole columns, whether T-tree or RNtuple. We don't have to read whole columns of data that the user's not interested in. But you do or might have to read all the metadata at startup. And we were talking about seconds. It's plausible that reading thousands of metadata for thousands of RNtuple fields could take seconds. That's plausible. But if your reading of the whole column is not significantly more than the seconds involved in reading the metadata, then the files are too small.
And Jim, I'm not a core Uproot developer, so you will have the final say on whether I'm off the wall here. We did in Uproot prior to November, we had a metadata bug that was leading to slower opening of some Uproot files. So if you're seeing seconds just to open a file and locate a T-tree, in part, I would say maybe look at that and check whether the latest Uproot release fixes that or halves the time, for example. Jim, is that relevant here?
Possibly. We dealt with large directories where we had an order n squared in the number of objects and fixed that.
Okay.
But those are large directories.
Directories, yeah, fine.
Right.
I come back to you if I see something similar.
Mm-hmm. Okay. Other questions? Okay. Well, thanks for everyone for coming.